Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Alright, Alhamdulillah. Allahumma salli ala Sayyidina Muhammad. Alhamdulillah. Today we are moving to chapter 4, which is amplitude modulations. We have covered chapter 1 and chapter 2. Chapter 3 is about MATLAB. Okay, so the MATLAB you cover in the lab session. Okay, so in chapter 4 we are talking about modulation. Okay, and what is modulation? Basically, is a process of a signal. So we are processing the signal that has a message or information which is represented by ST to be transformed into another signal. After we process, it becomes another signal. Why? To facilitate the transmission over a communication channel. So we know that there are two types of channel, wired and wireless. So in order for that particular signal to be transmitted, it has to be transformed or changed. Okay, so the message signal will be represented by ST will be transmitted or will be carried in a carrier. Okay, so the carrier is like a transportation for the signal to be transmitted to the receiver. So a carrier is identified. Okay, this is the basic general of a carrier. It must be A, has an amplitude A, or depends on the designer of the system, cos 2 pi FCT. FC here is the frequency of the carrier, plus theta if there is a phase also. So this particular signal is the carrier. Okay. So amplitude modulation, frequency modulation, and phase modulation will be types of modulation that we learn in this chapter. Okay. So for amplitude modulation, the amplitude of the carrier will be varied according to the message signal. So in order for the message signal to be bring okay, during the transformation, we put the information at the amplitude. Okay, the second one is the frequency modulation, where we change the frequency of the carrier. So we change this one in accordance with the message signal. So the message signal is located at the frequency of the carrier or varies in the frequency. And the third one is the phase modulation. So in here, which is the phase here, theta, the phase will vary according to the message signal. So there are three types of modulation that we will cover in this chapter. Okay, actually modulation can be analog modulation or digital modulation. Okay, so as I said before, the amplitude modulation, frequency modulation, and phase modulation we will cover in the subject fundamental of communication. So these three will be covered in the next semester. Okay, so why we should modulate? Okay, why we need to modulate? Okay, so the first one, we would like to transfer the message signal to a new frequency, which is we call frequency translation. So it has a new frequency depending upon the intended frequency of the transmission. So some channel can accept a certain frequency. That's why we want to change the message signal frequency to a new frequency. Okay, the frequency slot is determined by the frequency of the carrier. So the new frequency will depends on the carrier frequency. Right. Number two, we would like to have a division of a channel, or we call it a channelization, which enable a single communication system to share a channel, to share several channels by dividing it into lower bandwidth, or to represent a signal or a user. Okay, so for example, we have a number of user, but we want to put it in the same bandwidth, so we put the each of the user to a different modulation or carrier to enable it as a channelization. Means we channel it into smaller bandwidth. The third one is practical equipment design. That's mean certain transmitted signal accepted by a certain equipment or antenna. Okay, for example, we want the smaller antenna, so there is a frequency that can be acceptable for that particular small antenna. So that's why we have to change the signal or transmitted signal, the information into another signal, a new frequency, so it can be practical or be able to receive by the equipment. Okay, for your information, the smaller the antenna size is required for a higher frequency. Okay. It also said that narrowband electronics are easier to realize because some electronics system or electronics design accept a narrowband. So that's why we have to change it into a new frequency. Okay. The fourth one is performance improvement. That's mean if we increase the noise immunity, how? By expanding the bandwidth of the transmitted signal. So that's mean with the new frequency or the new modulated signal, it can reduce the noise and increase the noise immunity, right? So this is how it looks like in the real life application. For example, you have your voice here via microphone. Okay, so you need to modulate it for being able to be transmitted by the transmitting area. So the modulator will be helped by an oscillator. So the oscillator will generate a carrier here and process the signal with the carrier to be able to be transmitted in the antenna or aerial, and then when it receives at the receiving area or antenna, the signal it called modulated signal. Okay, when it has a modulated signal, we need to demodulate it back the signal in order for us to hear the sound. Okay, so since the signal will be attenuated, we also have an amplifier to get the signal get increase of the amplitude. Okay, just now I've mentioned three types of modulation: amplitude, frequency, and also phase. Okay, under the amplitude modulation, we have double sideband suppressed carrier, or it also called the amplitude modulation. But don't confuse with the second one because we also call it conventional AM. So just bear in mind that the first one is the double sideband suppressed carrier, DSB-SC. Okay. The second one is the conventional AM. The next one is SSB, single sideband. Okay, for the vestigial, basically we just use a filter which is similar to the SS band. So I just cover the three types of amplitude modulation. Okay, so the first one, DSB-SC, double sideband suppressed carrier amplitude modulation. Okay, some of you have seen this in the lab. Okay, so what is double sideband suppressed carrier means? We obtain the modulated signal by multiplying the message with the carrier. Okay, so as simple as that. So when we have a signal, okay, signal SST, we multiply it by a carrier, straightforward. Okay, so we call it as double sideband. Okay, why it's double sideband and why it is suppressed carrier? It will be answered when you plot the spectrum or frequency spectrum. Okay, so if you have a carrier AC cos 2 pi FCT, this is the carrier, okay? So you will have AC cos 2 pi FCT. This is the carrier. So what is the signal? It can be anything. Okay, this is the ST. Okay, so ST is information or message signal, and then we generate a carrier. It must be AC cos 2 pi FCT. So this device or this shows an oscillator. Okay, this oscillator will generate a carrier to the multiplexer. The multiplexer will multiply the ST and also the carrier. Okay. So when you multiply a signal, okay, the signal is in the form of any signal, okay, it shows here, but the carrier is a sinusoidal cos with 2 pi FCT. Okay, so the information is located at the envelope of the carrier and also multiplication of this message. So now this one is called the modulated signal. Okay. Okay. Let's see what is the spectrum of the DSB-SC. When you have a ST multiplied by CT in the frequency domain, you will have to convolve the S and also the C in the frequency domain. So let's say S is anything, okay? Multiplied by a carrier. So the carrier in frequency domain is 1 over 2, or this one AC, name it as AC, can be anything, divided by 2. This signal is convolved with the delta F minus FC plus delta F plus FC. So this part and this part is from the conversion of the carrier, which is AC cos 2 pi FCT. So that's why we have to know the Fourier transform of each signal, because in the communications representation, we will see the frequency of the process signal. Okay. Now, when a signal is convolved with a delta, that means you multiply and shifted that particular signal with the value of Fc. Okay, this is the value of Fc. Okay, and also plus Fc. Okay, right now if we have a signal SF, for example, in this example, SF is a triangle with a bandwidth from minus B to B. Okay, so when we multiply with carrier, that's mean in time domain we shift the frequency by Fc. Fc is the carrier frequency. So we move just now this one with Fc. So now the B having plus Fc and minus Fc and vice versa. Okay, Fc is the carrier frequency. Okay, now you see that it is called double sideband because it has one and two sides. So this one represented by this side, upper sideband and lower sideband, and also the other one is the upper sideband and lower sideband. And you see that the amplitude has now become half. Okay, amplitude has now become half. And one more important point in double sideband is the total bandwidth will become double also, 2B. Okay, one at this side and another one is at this side. Okay, now we have a signal AM cos 2 pi FMT. Okay, it is a simple signal cos 2 pi FMT with amplitude AM. Determine the spectrum of DSB-SC. So you know what is the carrier already, and now it given you a signal ST. So what we want to do now is to multiply the ST and also the CT. The question asks you for spectrum, okay, and also plot. So before we come to the spectrum, we have to find the modulated signal in time domain. Okay, so in time domain, the signal multiplied by carrier. Okay, so this is the carrier, and this is the signal, Okay, so when you multiply these two, that means you have to multiply cos and cos. So you need to have to use this formula. When cos u multiply by cos v, 1 over 2 cos u plus v plus 1 over 2 cos u minus v. So this is the conversion you need to change. Right now is cos and cos. Okay, so you also can have sine and cos. So you have to remember this Euler representation. Okay, now we want to multiply the amplitude. That means ACAM divided by 2. And the cos using this formula, 2 pi FC plus M, U plus V, and also U minus V. Okay. Now we have find the modulated signal in time domain. We want to find the frequency domain. So we do the Fourier transform. Okay. So when we have cos, that means we change into delta. So when we change into delta, it's going to be 1 over 2 delta F minus the frequency inside, plus delta F and the frequency inside. Also, it will have to, delta, 2 pairs of delta. So cos will be delta and another delta, and this cos will be delta and another delta. Okay, so that's why we have 1, 2, 3, 4. Okay, and remember also the amplitude 1 over 2 multiply the current conversion of cos become ACAM divided by 4. Okay, right now we are going to plot the spectrum of the DSB-SC. Okay, so when you see here, this is the spectrum of the signal, SF. Okay, spectrum of the signal is cos 2 pi FMT. So it has a energy at minus FM and plus FM. So multiply with signal and carrier, you got this value. So at minus FC minus FM, 1 delta, plus FC plus FM, 1 delta. The next one is minus FC minus FM and also plus FC plus FM. Minus FC minus FM plus FC minus FM, yeah. This one, the 1, 2, 3, 4. Okay, how about the amplitude? The amplitude is ACAM divided by 4. Okay, so right now you have all the information and answer for example 4.1. Okay, let's see also how we measure the power content in DSB-SC. Alright, so if you recall, how we find power is by we put a limit 1 to t, integrate that signal squared. Okay, integrate that particular signal squared. Okay, so we have just now s squared t, whatever the must be squared, and the carrier also cos squared 2 pi fct. Okay, when we substitute and do the derivation, we will have this power as is measured by AC squared divided by 2 multiply with the power of the message signal. So it depends what kind of signal we are using or transmit. Okay, so PS average power in the ST and AC squared divided by 2 is the carrier power. Alright, after we process the modulator at the receiver, it will come as a modulated signal, not the original signal. So what we have to do, we call the modulated signal as RT. Okay. So what we do, we'll we'll multiply the received signal by a generated carrier. So it's actually the same process. And then we will recover the signal by passing the product through an ideal low pass filter having bandwidth B. Okay, so right now at the receiver we will do a multiplication or multiply here with a carrier. So this carrier must be the same with the carrier that we use at the transmitter. Okay, so cos 2 pi fct. So when you see here, there are amplification of 2. Okay, why? Because when we see at the modulated signal, the modulated signal is divided by 2. Okay, so in order for you to multiply it back to its original signal, we have to, at the demodulator, we have to use double the amplitude to get the original signal back. So this signal is going to have also a double side. So we use low pass filter to just get the one side of the signal. Low pass filter will only take at frequency B. Okay, no need the either upper side band, take either upper side band or lower side band. No need the both side band. Okay, so this kind of process of the demodulation we call a coherent demodulation. Okay, so YT is actually the retrieve signal or the signal, the message signal. Okay, what we do is we multiply the received signal or modulated signal by 2 cos 2 pi fct. So that's mean XDSB multiplied by 2 cos 2 pi fct, the one that I have explained here. So when we have the two side, right now, remove this one using the low pass filter. Okay. In the process of demodulation, also we have an error. Okay, sometimes it's going to be shifted an amount of delta. Okay, delta F, and also the phase also offset about a little phi. Okay, at the demodulator. So this process is allow us to check the delta F and also phi that been shifted. Okay. If the delta F equivalent to 0, that means the desired signal is scaled by a factor that depends on the phase offset. So cos phi. So if there is a shifted by 45 degree, the amplitude of the desired signal will be reduced. So that is how we calculate or predict the desired signal reduction. Okay. If 90 degrees, it means the signal component vanish, mean very high error. Alright. So let's see problem 4.1. We have a signal of sine 100 pi t. The carrier is now cos 36,000 pi t. Okay. Now we want to generate the DSB-SC signal. So we have to sketch the spectrum of the message signal, which is this one, and also sketch the resulting DSB-SC. And also after plot DSB-SC, we can know which one is the upper and lower sideband. Okay. Then the next one, we have to use this as a signal. Okay, so for the signal, which is sine 100 pi t, sine 100 pi t, that means F is equivalent with 50 because 2 pi ft is equivalent to 100. So F is equivalent to 50. That means the Fm will be located at minus 50 and 50. But bear in mind, this is a sine, so it will be 1 over 2j. Okay, so 1 over 2j, and for a sine, is actually the amplitude is here, like. But since we have made it absolute value, now both are at the positive side. Okay, and then for question B, we want to do the DSB-SC process, which is we multiply S1 and also carrier. Okay, multiply using the formula cos A plus B, and sorry, not okay, for sine multiplied by cos, the formula is cos A plus B minus cos A minus B. Okay, so the plus and minus is the difference. So that's why you have this symbol. And then we have right now sine 36,000 is modulated. This sine will generate 2 delta, and also this one 2 delta. Okay. So this is the value of F by dividing by the 36,100 by 2F. Okay, and this one from the second part. Okay, right now we can plot in the frequency. So if you want to be safe, just put the magnitude as absolute value. So everything will be at the positive side. So you plot F 18.05 plus minus and 17.95 plus minus. So the right one is usually the upper sideband. At the negative side, the most left is the upper sideband, and the lower sideband is the at the left in the positive side and the right side of the negative side. Okay, for the second signal, which is cos 600 pi t, cos 18,000 pi t, so we have to do the module. First of all, we have to draw the signal. Okay, draw the signal. So in this one, we have 2 delta, and here also we got 2 delta. Okay. So this is the message signal. Okay, we can expect the modulated signal to be double of the bandwidth of the message signal, because the DSB-SC, the bandwidth is double of the bandwidth of the message signal. Alright, so again we multiply, so be careful with the calculation, because right now we have cos and cos multiply with cos. Yeah, okay. So you do part by part, and then you transform into frequency mean. Just now we have 4, now we have 8 delta. Okay. Alright, so the second problem is again the same process, but right now it's additional. The previous one is multiply. ST and CT. Okay, so find the modulated signal, spectrum, and also calculate the average power. Alright, so when we multiply the signal, this is the cos, this is the message signal, and this is the carrier. Okay, this is also the amplitude of the carrier. So you multiply one by one and get the modulated signal. So the next one, you have to do the spectrum by converting this cos into delta for its Fourier transform. Okay, right now we have identified the spectrum, and the last part is we have to find the power. Okay, so just now, how we want to find the power is by AC squared divided by 2. Okay, so the AC is AC squared divided by 2 multiplied by the power of each signal. Okay, here. Okay, so we have 1, 2, 1, 2, 3, 4, 5, 6, 7, and 8. Okay, if you see that this one is, the amplitude is 1 over 2, and the small one is 1 over 8. Okay, so there are 2, 1 over 2. Actually, there are 4, right? 1, 2, 3, 4. Okay, but why this is only 2? Because remember, the formula is actually divide by 2, yeah? Divide by 2 and multiply by 2 here. So you can just cross this one. Okay, so 1, 2, 3, 4. Now each of the particular signal, 1 over 2 is the amplitude of the first delta. Second, this is 1 over 8 divided by 2, and 1 over 8 divided by 2. So if you don't know the AC amplitude, you just put a AC, because in this example it gives you only AC. Okay. Okay, so I will stop until here for the DSB. The next class we will continue with conventional AM. Alright, with that I finish with tasbih kifarah and surah wal asr. Alright, thank you very much for listening, and assalamualaikum warahmatullahi ta'ala wabarakatuh.